Hello there, Mr. Sutton here, bringing you the AB Calculus Chapter 6 Quiz 3 review solutions on area and volume. For this problem, they want us to find the area bounded by the f of x and g of x curves. These are all calculator problems on this review, so let's go ahead and go to Desmos and graph this out. So here is Desmos. Let me set up my f of x, and that's going to be x squared minus 4x plus 1. And now for my g of x, that is negative x squared plus 2x plus 1. All right, so this is what we're dealing with here, this bounded area. So here's a picture of what we're trying to find the area of. And since we've got one top function and one bottom function, I think we can just stick with vertical left to right sort of integration with respect to x. So we're just going to get the limits of integration as x values. So it looks like 0 and 3, but we can go on Desmos if we want to be really sure. So yes, they intersect at x equals 0 and at x equals 3. So there we go. So we're going to take the integral then from 0 to 3 of, and I'm just going to do if I use absolute value in here, I don't really need to worry about which one is the top function and which one's the bottom function. Normally I would do g of x minus f of x because g is this top function here. But if I use absolute value, it wouldn't really matter which way I did it. But I'll do it this way just for, thoroughness sake. So going to my Desmos now and plugging this in. So we've got integral, int, 0 to 3. G of x minus f of x dx, and that comes out to exactly 9. And again, if you were really worried and had the use of a calculator, you could just use absolute value and not worry about the order of subtraction. For this problem, they want the area of the region enclosed by f of y and g of y. So let's go to Desmos and graph those out. So f of y, that's going to be y squared, and we can just take a better look at it. And then g of y, that's going to be y plus 2. So it's this enclosed region here. And because I'm going to be integrating with respect to y, since that's how this is set up, I don't have to, but it's going to be easier because there's one rightmost function and one left function. If I try to do this with respect to x, then I'm changing top and bottom functions a few times. So if I'm doing this with respect to y, I need the lowest and the highest points in the bounded region. So just going back to Desmos, if we want, they intersect at the y value -1 and +2, which it looks like on the graph. So these equal each other at -1 and +2 for the y values. So then I'm just going to be doing the integral from -1 to 2 of, we're going to do right minus left. So that's going to be g of y minus f of y dy. Going back to Desmos to do that, let me see if I can get a better look at what I just wrote. So we've got integral and then -1 to 2. Parentheses, g of y minus f of y, close parentheses, and dy is what we need in there, and that comes out to 4.5. For this problem, we're trying to find the region bounded by these curves, so let's go on Desmos and see what we're dealing with, clear out anything that's already in there. So we've got y equals square root of x plus 1, and y equals x minus 1, and y equals 2. Okay, so there's our region. There's a blown up picture of it. And if I want to do this using integration with respect to x, going left to right, so you'll notice that we're going to be changing our bottom function right here at 3. So we would actually need two integrals, one with this square root plus 1 minus 2, and another with square root of x plus 1 minus x minus 1. because of that change in bottom function. Another way to do this is to change these around to be in terms of y and integrate with respect to y, and then we just have a single integral that we'll need for that approach. So I'm going to show you that approach. So I'm going to rewrite these. For this first one, to rewrite it, solving for x, I would be subtracting 1 and squaring both sides. So I would say f of y equals y minus 1 quantity squared. That's this first one rewritten. To rewrite this next one, if we just solve for x here, I'm just adding 1 to the other side. So y plus 1, f of y, g of y actually, we'll call that one. Y plus 1 is what we can write that as. And I'll just go on my calculator and rewrite these as I did up there. So I'm going to have, again, f of y, and that was, what did I say? Y minus 1 squared. Y minus 1 squared. There we go. And then we've got g of y, which we said was y plus 1. And I've got the exact same bounded area, a little bit more going on with this f of y function than f of x had, but that's okay. All right, so what do we do next? Well, if I'm going with respect to y, I need my limits of integration. The lower y value is right here. That's going to be 2. And to get this upper limit of integration, I need to see where basically f of y and g of y intersect. It looks like 3. It probably is. I'm going on the calculator just to double check. Yep, that is the y value 3 up there. So I'm going to have the integral then from 2 to 3 of, this is the g of y function. The left one here is the f of y. So I'm going to do g of y minus f of y, rightmost minus leftmost. And that's going to be dy there. Go into the calculator to implement that. Let me just give myself a little more room. So we have integral 2 to 3, parentheses, g of y minus f of y, close parentheses, dy, comes out to 1.167. On this problem, I'm trying to find the volume of the solid obtained by rotating the region bounded by these functions about the x-axis. So let me go to Desmos and see what these look like on a graph. And I don't really need Desmos to graph these, but why not? I'm going to be using it anyway for the number crunching. So we have f of x equals square root of x, and then we have y equals 0, which is just the x-axis, and we have x equals 6, a vertical line through 6. So this is the bounded area that we're looking at, and we're revolving around the x-axis, which is one of the boundaries of my bounded region. So there it is. There's the area I'm revolving around the x-axis. Because my bounded area is flush with this axis of revolution, that means I can use washers, or not washers, disks. I can use disks, pancakes, for my area formula. So I'm going to write a of x equals pi r squared, and then my radius is just the distance from the axis of revolution to the outer part of the bounded region here, which is just the f of x function. So this is just pi times f of x squared. So I'm going to take that area function and integrate it over the interval from 0 to 6. So 0 to 6, a of x dx, which I've already written out. And all I need to do now is plug some things in the calculator. So going back and clearing out what so I can see here, I'm going to write my a of x function first. That is going to be pi times parentheses the f of x function I already defined, and we'll square that. And then I'm going to want the integral from 0 to 6 of a of x dx. Comes out to about 56.549. On this problem, I'm trying to get a volume of the solid found by rotating this bounded region about the x-axis. Let me start by graphing this out. So on Desmos, I've got, we'll call it f of x equals x to the 4th, and we also have the line y equals 2. So that's what we're dealing with, is this area in here. Now if I'm going about the x-axis down here, there is a bit of a gap between parts of my bounded region and the x-axis, the axis of revolution in this case. So I'm going to need washers or donuts in order to get the area for what I'm going to be integrating here. So for my area formula, I'm going to write a of x equals pi times big R squared minus little r squared. Big R in this case is going to be the further away part of the bounded region from the axis of revolution. So that's going to be this distance here, which is 2 minus 0, or just 2. And then for little r, that's going to be the inner part of the bounded region, the distance between that and the axis of revolution. So in this case, that's just the f of x function, minus 0, which is just the f of x function. So minus f of x squared. And that whole thing is my area formula. Now, before I can actually get anything else, I need to figure out my limits of integration. So we're trying to figure out basically this spot and this spot here, the places where x to the fourth and 2 have the same value. So what x value would give me 2 as a result? Well, I could go on Desmos and calculate this, and I'll just show you what it looks like. Here you go, crazy decimal, positive version of crazy decimal. That crazy decimal is just the fourth root of 2, plus and minus that. So either way, totally up to you which one of these you use, but I'm going to just plug in fourth root of 2 because that's the most accurate representation of that point. But you could copy that decimal and use that too. So I'm going to have the integral from negative fourth root of 2 to positive fourth root of 2 of a of x dx. And now let's implement all of this on Desmos. All right, so let's see here. Let me get my a of x formula, and maybe if I move this over here, I'll be able to see it. There we go. Now I can see. So we have a of x equals pi, parentheses, 2 squared, which I know is 4, minus f of x, and square that, and then close the parentheses. So there's a of x. And now we needed to do the integral, int, and we need a negative fourth root, so that's negative nth root. Put a 4 up there, put a 2 there. I'm going to copy and paste the fourth root so I don't have to write all that again. So I've got positive fourth root up there, and in here I've got a of x dx, which comes out to about 26.567. On this problem, I'm trying to take the region bounded by f of y, y equals 1, and x equals 0, and get a solid of revolution, get the volume of that by rotating it around x equals negative 3. So let me graph all this out and see what we're dealing with. So on Desmos, let's clear out all this garbage that's in there from before. So we've got f of y equals square root of y, sqrt of y. And then we have y equals 1, x equals 0, which is just the y-axis right here. And we've also got x equals negative 3, which, let me show you, if we move over a bit, there's negative 3. And if we really want to, we can make that like a dashed line just to show it's not actually part of the bounded region, it's an axis of revolution. So there was my picture. This is the bounded region, and I'm revolving this around this axis all the way over here. So in order to make that happen, I'm going to have to use washers. There's a big gap here between the bounded region and the axis of revolution. So I've got a of y. I've got to integrate with respect to y here because this is a vertical line. That's going to be pi big R squared minus little r squared. Big R is the distance between the outer part of the bounded region and this line over here. So that's going to be f of y minus negative 3 or plus 3, and we're squaring that. Little r is the distance between this part of the bounded region and the axis. So that's just 0 minus negative 3 or just 3, and we're subtracting that squared. So there's my a of y. For my limits of integration, we're going from 0 to 1. So I need the integral from 0 to 1 of a of y dy. Let's go and plug all of that in now. So let me get my area formula. A of y equals, and over here we've got pi times parentheses f of y plus 3 squared minus 3 squared. So let me do a squared parentheses minus 3 squared. And let me just go back and fill this in with f of y plus 3. There we go. Let's make a new entry. Now I need the, whoops, see if I can see what I wrote there. Integral from 0 to 1 of a of y dy. Integral 0 to 1, a of y dy, and that's going to be about 14.137. For this problem, the base of a solid is the region enclosed by the semicircle, y equals square root of 81 minus x squared in the x-axis. Cross-sections perpendicular to the x-axis are squares. We want the volume of the solid. Well, let me just take a look on Desmos at the part that I'm graphing here, and I'll just put this in as f of x. In fact, while I'm at it, let me just define f of x as this square root of 81 minus x squared. All right, going to Desmos. Let's plug this in. F of x equals square root 81 minus x squared. And might need to zoom out a little bit here. There we go. So we've got this semicircle. We're going left to right, and they said the cross sections were squares. So we have these squares growing out of here. So let me get an area formula for those squares. In general, the area of a square is going to be s squared. Now the base of the square that's growing out of here, this is the distance between the semicircle and the x-axis. So it is just this f of x function here. So when I write s squared, I can really just say f of x squared. So there's my area formula. I need my limits of integration. That's where this semicircle is hitting the x-axis, and that's happening at -9 and +9. So f of x equals 0 at plus or minus 9. So I will need the integral then from negative to +9 of this a of x dx that I just wrote. And let me do that on the calculator. So let me do a of x equals, and we're going to do f of x squared. And then we need integral -9 to +9 of a of x dx. Comes out to exactly 972. For part B of this, we have a solid enclosed by y equals -x squared plus 9 and y equals 0. Cross sections to the perpendicular to the x-axis are rectangles, heights 6 times the side in the xy plane. So let me define this as f of x here. We'll call that -x squared plus 9. Let's just graph that on Desmos to again see what we're dealing with. And also I'm going to need f of x defined anyway on Desmos. So this is just an upside down parabola, and y equals 0 is just the x-axis. So we have these rectangles growing out of this thing going from left to right. Now the area formula for a rectangle, that's going to be in general base times height. And they said that the height was 6 times the side in the plane, so 6 times the base. So this is really b times 6b, or 6b squared. And since the base of these rectangles is just the distance between f of x and 0, we can just write this as 6 times f of x squared. Now what are my limits of integration? Well, f of x is going to equal 0 at -3 and +3. We can pick that right off the graph. So I'm going to need the integral then from negative to +3 of this a of x dx that I just wrote. Let's go to Desmos and put all that in. So let me do my area formula. A of x equals, we said 6 times f of x, that whole thing squared. So I need integral -3 to 3 of a of x dx, and that's coming out to about 1,555.2. On this one, we want the volume of a solid whose base is the region enclosed by this semicircle and the y-axis. Cross-sections perpendicular to the y-axis are semicircles. All right, so let's define this as f of y equals 16 minus y squared, just so I can use it. Let me graph that on Desmos and see what the deal is. We got f of y equals square root 16 minus y squared, and that's what we're looking at. So we have some semicircles growing out of this thing in a bottom to top sort of fashion. To get the area formula for these semicircles that are coming out of this semicircle, in general we have 1/2 pi r squared. Now the radius of these things is going to be half the distance from the y-axis to the f of y function. So I'm going to need to do f of y over 2 for that. So I'm going to write 1/2 times pi times half of f of y quantity squared. And for my limits of integration, this is going to be where f of y equals 0. That's happening at the y values -4 and +4. So then my integral, I'm going to need the integral from negative to +4 of a of y dy. And the rest of the heavy lifting is going to be done on the calculator. So we have a of y equals 1/2 times pi times, I'll do a squared parentheses, and inside there I've got half of f of y. And now let me do my integral from -4 to 4 of a of y dy. Comes out to about 33.510.